So in this video, we're going to be talking about something called differential equations. So we'll get into what that means in just a minute. But I just wanted to kind of give you a little preview of what the remainder of the quarter is going to be like. So this topic that we're covering in this video is actually a very extensive topic, but we're really just going to do kind of a simplified, brief version of it. And the same thing is going to go for the remaining topics in the class. So, we just don't have the time in this course to really get deeply into a lot of these topics. So the rest of the quarter, we're going to kind of briefly touch on a variety of topics. So we're going to talk about differential equations. That's what we're doing in this video and the next video. Then we'll spend 2 videos talking about parametric equations and calculus with parametric equations. And then the last 2 videos of the quarter will be about polar coordinates and polar equations, as well as calculus with polar coordinates and equations. So, I don't want you to be intimidated because I know it is a lot of different topics, but as I said, I'm going to really try to simplify them as much as I can and just make it kind of like, a brief glimpse at these different topics. Okay, so what is a differential equation? A differential equation, well, it's an equation, right? It has an equal sign in it, but a differential equation is an equation that relates a function with its derivative or derivatives. So I just want to give you a few examples of what a differential equation might look like. So one example of a differential equation would be y prime is equal to x times y. Another example would be dy dx. So you can either, sometimes with differential equations, you'll see them written with y prime. Sometimes you'll see them written with dy dx. So dy dx is equal to x plus y squared. Sometimes they also involve second derivatives. So another example could be 2y double prime, so the second derivative, plus y prime minus y is equal to 0. And then one last example could be something like x times y prime is equal to y plus x squared times sine of x. So in this class, and not necessarily in this video, but in the next video, we're going to be learning how to solve some types of differential equations. So what do I mean by solve them? I mean find a function y that satisfies these equations. So we'll focus more on that in the next video. But I just want to say up front that, most of the equations I wrote down on this sheet, we actually are not going to learn how to solve in this class. So differential equations is actually a really big topic. You can take multiple classes about it. It's almost like calculus, right? Like you have Calc 1, Calc 2, Calc 3. There are like multiple different classes that you can take about differential equations. So this is, again, just a very brief glimpse of what differential equations is about. But yeah, so like I said, in the next video, we'll learn how to solve certain types of differential equations. But in this video, I want to just kind of focus on getting a little bit of kind of intuition for what is the meaning of a differential equation. So we're gonna look at some kind of simpler examples than the ones I wrote up here and try to just kind of interpret what they're saying and see if we can use that kind of interpretation to find a solution to them. So I'll kind of describe this as, what does a differential equation, or I'll say it this way. Interpreting differential equations. So one thing that I think is just a really important skill in general in math is being able to look at an equation or, a theorem or a formula and not just read it as a bunch of math symbols, but really try to kind of read it in words. So for example, what if we had the differential equation dy dx is equal to x squared? So let's try to literally, without saying any kind of math symbols, well, we'll have to say some, but let's try to kind of translate this into a sentence. What is this equation saying? Well, what does dy dx mean? That means the derivative of y with respect to x. So the left-hand side of this is saying the derivative of y, and I'll abbreviate, people often use WRT as an abbreviation for with respect to x, is x squared, right? That's how you could kind of read that sentence out loud. So what does it mean to solve an equation? Well, you might think of solving an equation as, oh, you do algebra, but that's not really what it means to solve an equation. To solve an equation just means to find a solution, right? To find something that makes this equation true. So in the next video, as I mentioned, we'll focus on kind of like algebraic methods of solving differential equations, but this one we can actually solve just by kind of thinking about the meaning. So what would be an example of a function y that would make this true? You know, what is an example of a function y such that the derivative of that function is x squared? Well, that's actually exactly what we've been doing in this class, right? It's taking an antiderivative. So in this case, we could say that the solution would be y is equal to x cubed over 3 plus c, right? Because that is an example of a function y such that the derivative of that function is x squared. So one thing that's kind of good to keep in mind, and we'll see this a lot in more detail in the next video, is that anytime you're solving a differential equation, there's generally going to be infinitely many solutions. And sometimes people describe it as a family of solutions, right? Because there's not just one function y that has a derivative of x squared. You could have x cubed over 3 plus 1. You could have x cubed over 3 minus 10. You could have x cubed over 3 plus a million. You know, really you can add any number onto this and it will still be a solution of this differential equation. Okay, so let's look at another example. So let's say that now we're trying to interpret and then see if we can find a solution to the following. So y prime is equal to y. So first step, what I want to do is kind of translate this into a sentence. So there's no x's in this, but we can still assume that we're thinking of y as a function of x. So we can still say the derivative of y with respect to x is, well, this says it's y. So what does that mean? What does it mean to say the derivative of y is y? That basically means that we're looking at a function where when you take the derivative, it's the same function as what you started with, right? So another way of saying this would be y is a function that does not change when you take its derivative. So can you think of an example of a function that does not change when you take its derivative? Well, the first one that might pop into your mind is e to the x, right? So one solution, one example of a solution would be y is equal to e to the x. So in this case, we actually cannot put a plus c here because then this statement wouldn't be true anymore, right? So if you start with e to the x plus 5, for example, then the derivative will just be e to the x, and that won't be the same as what you started with. So in this case, the plus c would actually be in the exponent. And so why is that? Well, it's just because, think about it, if you start with, so an example would be y is equal to e to the x minus 1. You know, what's the derivative of e to the x minus 1? Well, it's just e to the x minus 1. Right? Or you could just have y is equal to e to the x, or you could have y is equal to e to the x plus 100. You know, if all you're doing is adding or subtracting something from x in the exponent, that's not going to change the derivative. So anything that's of this form is going to satisfy our equation. Okay, let's look at one more example of one that we can just kind of like reason through. So next one is similar to the last one. So y prime is going to be equal to 2 times y. So what does that mean? That means that the derivative of y with respect to x is 2 times your original function y. So let's try to think of an example of a function where when you take its derivative, you don't get exactly the same answer, but you get 2 times your original function. So this one actually is very similar to the last one. So what if we, if we try y is equal to e to the x, that's not going to work, right? Because the derivative of e to the x is e to the x. And so that is the same as the original. We want one that when we take the derivative, we get something that is 2 times the original function. So how can we kind of get this 2 times the original function? Well, if we do e to the 2x, right? Because what happens when you take the derivative of e to the 2x? You get e to the 2x times 2, which is 2 times your original function. So we could add something here. We can really say plus c, because again, because of how the chain rule works and because the derivative of a constant is 0, if you have an extra number being added in the exponent, that's not going to affect the derivative. So for example, if you let, let's say y equal e to the 2x minus 5, what's the derivative going to be of that? Well, it's going to be 2 times e to the 2x minus 5, just because of how the chain rule works. So it gave us not our original function. So here's our original function. It gave us 2 times the original function, and that's exactly what we were looking for. So, these aren't, I don't think there's any that are like this on the homework or anything, but I do think that this is a really good way to kind of build understanding of what differential equations are saying. And to me, I almost feel like this is more important than being able to do the algebra of solving. Just being able to understand like what is an equation saying and being able to kind of interpret it into plain language. But there's limitations to this, right? There's, most equations we would not be able to solve this way. So for example, if we go back to some of the ones that are at the top, those are not ones that we could solve this way, at least not easily. So the next thing I want to look at is verifying that something is a solution. So again, we're not really getting so deeply into solving these in this video. That's going to be more in the next video. But one thing we can do is if you're given a differential equation, you should be able to verify that something is a solution to that differential equation. So the first example I want to do is I want to verify that I'm going to use some color coding here. So y is equal to negative e to the negative x is a solution to, and so we're going to look at the following differential equation. So it's going to be 2 times y double prime plus y prime, minus y is equal to 0. So how do you verify that something, forget about differential equations for a second. How do you verify that something is a solution? Well, you plug it in, right? If you have like a linear equation and someone asks you to verify that something's a solution, you would plug that point into the equation and show that it gives a true statement. And so what we want to do is, we already know what y is. Now we just need to find y double prime and y prime, and then we can plug those in. So, we want to start with y prime, right? So what is y prime? Maybe I'll write down y as well, even though we have it above. So we know that y is equal to negative e to the negative x. What is y prime? Well, we would need to, bring this negative sign along, but then we would use the chain rule, and we would get negative e to the negative x. And so altogether, that would actually give us positive e to the negative x. And then what about y double prime? Well, now we would take the derivative of y prime, and so we would use the chain rule, and we would get, again, back to negative e to the negative x. And so now how do we verify that this is a solution? Well, we just plug each of these things in and see whether we get 0. So 2 times e to the negative x plus, so for y prime, we just had e to the negative x. And then for y, we had negative e to the negative x. So let's see what this, and I guess we're kind of trying to figure out, is this equal to 0? So if we multiply this together, we get negative 2e to the negative x. And then here we have e to the negative x plus e to the negative x. And so now we have negative 2e to the negative x plus 2e to the negative x. And we're seeing if that equals 0, and it does, right? 0 is equal to 0, so we just verified that this is a solution. So what will be the case in many differential equations, and we already kind of talked about this, is that there's multiple solutions. And the multiple solutions might not look exactly what you think. So it might not always just be like, plus c. So I want to show you another equation that would work here. And by the way, on your homework, there's a couple of questions where they ask you basically find all of the ones that are solutions. So it will give you like a list of different possibilities for y to try, and there's going to be more than one that work. And so you have to kind of test each of them by plugging them in, and you can't just stop when you get one that works because there might be other ones on the list that also work. So let's do the same thing, but now we're going to verify that. So this time we're going to do y is equal to 3e to the x over 2. We want to verify that this is also a solution. So again, let's go through and write down our derivatives. So we have, the original one was y is equal to 3e to the x over 2. The first derivative, what color did I use for that? Orange, I think. So the first derivative would be, so we would have 3, and then when we use the chain rule, we would get a 1/2 from the exponent. So we'd get 3 times 1/2 e to the x over 2. And so that gives us 3/2 e to the x over 2. And then the second derivative, well, we would again have something come down from the chain rule, right? So we would have 3/2 times 1/2 times e to the x over 2. And that simplifies to 3/4 e to the x over 2. So let's plug that into our original differential equation. So the differential equation again was 2 times y double prime plus y prime minus y is equal to 0. So we first plug in our y double prime, so that's 3/4 e to the x over 2. And then for y prime, we got 3/2 e to the x over 2. And then for y, we had just 3 e to the x over 2. And we're verifying, we want to check that this actually gives us 0. So if we multiply this out, here we get 2 times 3/4 is 3/2. So we have 3/2 e to the x over 2 plus another 3/2 e to the x over 2 minus 3e to the x over 2. And so if you add together these 3/2, you end up with 3e to the x over 2 minus 3e to the x over 2. And now we can see that that does in fact give us 0. So one thing you might notice is that there's just something nice about exponential functions because of how the chain rule works and the fact that they kind of repeat themselves. They really lend themselves well to differential equations that look like this one, because you're kind of getting these very similar things that can be added up and subtracted from each other in kind of a convenient way. So I want to share an application of differential equations that's something you have probably encountered in previous math or science classes, and that's the idea of population growth. So how does a population grow? Well, there's one kind of fact that really informs the way that we usually mathematically model population growth, which is that the growth rate of a population is what's called directly proportional, and I'll explain what that means in a moment, to what the population is. So population growth is modeled using the idea. So when I say modeled, that just means that, we can't make an equation that perfectly tells you exactly what a population is going to be after a certain amount of time. So modeled just means that, we're approximating it. So population growth is modeled using the idea that the rate of change of a population is directly proportional to the population, to what that population, how big that population is. So again, we want to kind of write down an equation that makes this a little more concrete, but first I just want to give you another way to kind of think about this sentence. So what does this mean, that the rate of change of a population is proportional to the population? It basically means that the bigger the population is, the faster it grows. Which kind of makes sense, right? Like it's, this is what you might think about when you think of exponential growth, right? Like the more something increases, the more its rate of change also increases. And that just makes sense with how population growth works. The more people or the more, whatever type of animal you're looking at there are, the more that population will be able to expand. So how can we translate this, this sentence that's written at the top into an equation? Well, the rate of change of a population, that would be dp dt. So let's say that p represents the population after, t years or whatever the time units are. So dp dt would then be the rate of change of the population. And then what does this word directly proportional mean? Well, it basically means that there exists some number k such that when you multiply that number k with the population, you get the rate of change. So directly proportional just basically, so maybe just to give kind of a side example, if I were to write down the sentence, x is directly proportional to y, all that means is that x is equal to k times y for some y. So directly proportional just means that there's some kind of a number that relates these two things via multiplication. So in some cases, it could even, it could be like x is equal to 2 times y, or x is equal to 5 times y, or x is equal to y, or anything like that is directly proportional. So let me just add here, for some number k. So basically what we're saying again is that, the bigger the population gets, the bigger the rate of change of the population is going to get. So another thing that you might have learned about population growth is that it can be modeled using a particular equation. So you may have learned that population can be modeled by the equation P is equal to C times E to the RT. And there's a lot of things that can be modeled with that equation. You might have also seen it in the context of interest, so earning interest in a bank account. But the same equation also works for population growth. And so C here would represent the initial population, and R just represents some kind of a growth rate. So this is an equation that, at least for me, I feel like I saw this in many math classes over the years, coming up as kind of an example. So what I just want to do is basically show you the connection between this equation that you've probably seen at some point and this statement at the top, which we also kind of rewrote as a differential equation. So what happens if we take this equation and we kind of take the derivative and compare it to the original equation? So if P is equal to C times e to the RT, then what's the derivative of that? Well, it's equal to C times, and then we have to use the chain rule, right? So R is just some number, and so we can bring down that R as our kind of chain rule part of the derivative, and so we get CR times e to the RT. And so what is that? So the derivative of our function is actually very similar to our original function, right? We could rewrite this as R times C e to the RT, right? So what did we just show? We showed that if you take this population equation, it actually does satisfy this differential equation up here, right? The differential equation we wrote down is that the rate of change of the population should be directly proportional to the population function. And we just showed that. We showed that if the population is modeled using the equation P is equal to C e to the RT, when you take the derivative, you get a number, R, times the original function. And so this tells us that the population function P is equal to C e to the RT is a solution to the differential equation that said dp dt is equal to some number k times the original function p. So this isn't something I'm going to test you on, but I just thought it was kind of an interesting thing to see, this interesting connection between this, idea that population growth works the way it does, right? The bigger a population is, the faster it grows. The fact that that really is basically synonymous with this idea that population is modeled by an exponential function. All right, so one last example, or one last kind of topic I want to look at. And this is actually, it's in its own section in your book, so I'll label it that way, but we're not really going to get too into depth into this. So this is something that's called slope fields. Oops. So in your book, this is section 9.2. So the idea behind a slope field is, let's say that you don't know how to actually solve a differential equation. So I'm going to write an example of one down here. So suppose you want to get an idea of what solutions to the differential equation. So the differential equation we're going to look at here is y prime is equal to x plus y. So we'll see in tomorrow's video, in the next video, we're going to learn some methods for solving differential equations, for actually, just doing algebra and just finding a solution in a way that will feel kind of maybe a little bit more clear. But this one we'll actually see we don't know how to solve. We're not going to, in this class, learn a method for solving this differential equation. So what can we do instead? Well, we can just kind of interpret what this is telling us in terms of the idea of slope. So another way of saying this, y prime is equal to x plus y. What does that mean? That means that if you go to a particular point xy, the slope, so the slope of the tangent line, right? Because that's what y prime means, right? Y prime means the slope of the tangent line at a point xy is equal to x plus y, right? That's all I did in this lighter purple is I just took this equation and I kind of rewrote it in words. So y prime means the slope of the tangent line at, a particular point. And then the right-hand side says, well, that's going to be equal to whatever the x coordinate is plus the y coordinate. And so what we can do is we can kind of like pick a few key points and start to kind of sketch what the slope would look like at those points by adding together the x and y coordinates. And then that will start to give us a picture of what the different solutions to this differential equation might look like. So let's do that. So we're going to do, I think, like 9 different points, but these will be quick because all we're doing is adding together the x and y coordinates. It's not going to take very long to do each of these. So for example, let's start with the point 0, 0. So at the point 0, 0, y prime is going to equal 0 plus 0, right? Because the slopes are both 0, or sorry, the x and y coordinates are both 0. So what does that tell us? That tells us that at a point 0, 0, if the point 0, 0 lies on the graph that we're talking about, we're going to have a slope of 0. So the graph is going to be kind of flat if it goes through the origin. Now let's try 1, 0. So, and one thing that's important to notice here, or note here, is that differential equations have many solutions, right? They don't just have one. And so we're not saying that one particular graph goes through all of these points that we're doing. We're saying, well, if you have a solution that happens to pass through the point 0, 0 or the point 1, 0 or each of these separate points, then it will have a shape like this. So I'll show you something that I think will help you visualize this a little better in a minute, but the picture we're going to get here is not just going to be the picture of one graph. It's going to be basically a shape that multiple graphs could kind of fit within. Okay, so what about 1, 0? So if we go to the point 1, 0, y prime is supposed to equal the x coordinate plus the y coordinate, which is 1. And so that means that if we have a solution to this differential equation that passes through the point 1, 0, it should have a slope of 1. So I'm just going to kind of draw that in here. Maybe I'll make this one a little bigger too, just to emphasize it. Okay, what about the point 2, 0? Well, if you have a point on the graph that goes through 2, 0, then the slope should be equal to 2 plus 0, which is 2. And so slope of 2 is going to look more like this. And maybe let me make that a little smaller. Okay, so let's try a few more points. So what about if we had the point 0, 1? So 0, 1, y prime is going to be equal to 0 plus 1, which is 1. And so that means that at 0, 1, we're also going to have a slope of 1. And 1, 1, we would have 1 plus 1, which is 2. So that means that at the point 1, 1, we're going to have a slope of 2. So the graph is going to look more like that. And then we can also do the point 2, 1. And so there, y prime would be equal to 2 plus 1, which is equal to 3. So one thing you might notice is that basically as you make the x and y coordinates bigger, the graph should get steeper, right? Because you're adding together the x and y coordinates to get the slope. And so therefore, the bigger the x and the y coordinates are, the steeper the slope is going to be. So let's go to the point 2, 1 and try to sketch one with a slope of 3. So that would look more like, oops, let me do that a little better. Maybe like this. Okay, so now a few more. Let's do the point, let's do 0, 2. So everything with a y coordinate of 2. So 0, 2, the derivative, the slope is going to be 0 plus 2, which is 2. So if we go to 0, 2, we're going to have a slope of 2, so like this. If we go to 1, 2, we're going to have a slope of, again, 3. So at the point 1, 2, we're going to have a steeper line with a slope of 3. And then at the point finally 2, 2, the slope would be equal to 2 plus 2, which is 4. So 2, 2, we're going to have like the very steepest one yet. Okay, so this probably looks like a bunch of nonsense. What are all these lines? So I'm going to show you a picture. I don't want to take the time in this video to calculate a gajillion of these. So I'm going to show you a picture on Desmos, and you can use this tool yourself if you just Google like Desmos. So these are called slope fields. So slope field generator. You will see that there's something, and sorry, I'm going to do kind of a side by side, and I'll tell you what this left-hand side is in a second. But this right-hand side here, so if you enter in your differential equation, so it says g of x, y, just think of that as being dy dx or y prime. So I just put in x plus y because that was the right-hand side of our differential equation. And so it gave us this whole kind of bigger slope field. And if you look at like the kind of just the area right here, that looks like what we found, right? So we were focusing on just from 0 to 2, so this little 2 by 2 window, and that's pretty similar to what we see happening. That would be like this little snippet right here. So how do we interpret this picture? Basically, there are many, many solutions to every differential equation. And so I don't want you to think that one curve goes through all of these, slopes that we drew. What this is saying is that if you have a solution that passes through these points that we delineated, then that graph must have the given slope. And so you can picture, there are many, many different functions that are going to be solutions to your differential equations, and you can kind of imagine tracing them out. So for example, you might have one that kind of looks like this. Just watch my mouse, I'm kind of tracing. Or you might have one that looks kind of like this. Or you might have one that looks kind of like this. So any solution you have basically has to kind of fit with the pattern of slopes that you're seeing here. So what I'm now going to show you on the left is some actual solutions. So as I mentioned, we don't actually know how to solve this differential equation. I just used a calculator to find the solution. And so solutions of the differential equation, y prime is equal to x plus y, happen to be functions of the form y is equal to negative x minus 1 plus c times e to the x. And so that number c is allowed to vary. So what I'm going to do now is I'm going to change the value of c. And I want you to kind of see whether you can see how, I'm saying see a lot, see if you can see how as I change the value of c, the graph that we have kind of fits with the picture on the right. So you can already see on this example, right, it kind of, you could imagine it fitting in like right here. It kind of fits with the shapes that we see. And so as I pull c to be bigger and bigger, again, we can see getting these graphs that maybe would fit higher and higher up here. And then what happens if I make c smaller? Well, eventually the shape of the graph actually changes and it becomes more like this. And so that also fits into our picture because that would be something that looks more like, if you watch my mouse on the right, kind of that goes down like this. So any solution you're gonna get is going to fit somewhere into this picture of slope fields. So I know this is very different and maybe a little confusing. Again, it's not something that I'm really emphasizing or that I want to spend that much time on, but I just want you to kind of get an intuitive sense of, again, what does a differential equation tell you? So in this case, we're kind of understanding what the differential equation tells us by interpreting what it's telling us about a slope of a tangent line. So I just want to point out, there's a homework question about, just one about slope fields, and I just wanted to pull it up quickly. So first of all, I apologize. I know it looks really confusing. There's, I think, 4 different options of graphs and they're just like really smushed next to each other. I couldn't figure out a way to change that. So unfortunately, that's how it is. But so this asks us, which of the following is a slope field for the differential equation y prime is equal to 1 plus x minus y? So how can you tackle this question? Well, I would start by an easy point. So for example, you could start with the point 0, 0. So when x is equal to 0 and y is equal to 0, you would get y prime is equal to 1 plus 0 minus 0. So y prime should be 1. So you could then look through these 4 options and see, do all of them have a slope of 1 at the origin? And these actually all do, right? All of these pictures look like they have a slope of about 1 at the origin. So let's try another point now. So now maybe let's try another easy point. Let's try 1, 0. So what would happen if we plug 1, 0 into this equation? We would have y prime is equal to 1 plus 1 minus 0. So that would give us 2. So the slope at the point 1, 0 should be equal to 2. And so in this graph, the one that's already selected at the top, this one does look like it has a slope of 2 about, right? If you look at this little snippet right here. But if you go down to this next graph, this one has a slope of 0. And so we can eliminate this graph. If you look at the next one, this also has a slope of 0, right? So we can get rid of this one. This one at the bottom, this one does also look like it has a slope of 2. So we're already down to 2 choices, and then you could just pick another point to plug in. So maybe plug in the point 0, 1, or plug in the point 1, 1, and just see what you get for your slope and kind of try to match it up with the remaining options and see which one matches. And one other thing I just want to mention, and hopefully you've figured this out yourself, but on any questions with graphs, if they have this little magnifying glass, you can pull it up and get a better picture. So I know it's a little confusing to look at them all at once, so you can also kind of pull them up and look at them individually. All right, so that is it for this video. Like I said, I know this was kind of a whirlwind of different ideas, but I'm not going to ask you to really go too deeply into any of these ideas. It's just kind of getting a sort of a vibe of what's going on with differential equations. And in the next video, we'll get a little bit more specific about actually solving them. So I'll see you in the next video.